All right. Oh, it says live now.
Now we are
Wow.
live. In principle, everyone with that link could follow this presentation.
All right.
By the way,
So I should behave properly.
I will cut away the first part if you don't mind, if you want.
What? Sorry?
I have the chance to cut away whatever you don't like.
Okay. Do you see my mouse too? Not very well, huh?
Yeah, you can't move it too fast.
Probably, I mean, the problem is that the mouse is black and my background is black too.
Did Charlotte have the? Did Charlotte want to come, or was he busy?
He mentioned like he was coming.
I think it's the. So Petra, how's the summer so far in Michigan?
How's the what?
Late spring, early summer, how's the summer in Michigan?
It's very green. I went on my first bike ride yesterday, which is kind of late because I was traveling. So I usually go earlier. But yeah. It was a lot of fun to a place called Schmidt's Corner.
I know.
Anyway, yeah, it's very beautiful here. Very pretty right now. Summers are great here. Winters too. Some people actually like a lot of snow. I'm not one of them.
Yeah, I think people here cannot really, even for Europeans, the amount of snow you describe every year is kind of, can't wrap your mind around that actually.
Yeah.
The coldest day since recording a couple of days ago was 80 degrees Celsius. Well, recording apparently started 14 years ago.
You said 80? 80?
8.
8, wow.
Yeah, it was pretty cold.
It's warmer here.
Well, here's it's winter next week, right? So,
No, not yet.
not yet. A few more days. Yeah.
It's La Nina, right? La Nina?
Yeah, is it Nina or is it El Nino? I don't know.
Whatever.
La Nina is over.
One or the other. Well, at least we got a lot of rain due to that. That's true.
Yeah, I think La Nina is now. They think there's one coming, and that means colder temperatures.
I see. Okay, it's 1:35. I think we should start. Yeah, today's presentation, Petra Huentemeyer, Professor Petra Huentemeyer, agreed to show us a little bit about her work, field of work, gamma ray astronomy. For those of you who do not know Petra, Petra studied physics in Germany at the University of Münster. She obtained her PhD in 2001 from the University of Hamburg. And in the following year, she moved to Utah, where she was a postdoc on HIRES and the Flash experiment. Then 2006 until 2008, she worked in Los Alamos on the Milagro Gamma Ray Observatory. And then since 2009, she is now a professor at Michigan Tech. And she is currently leader of the Galactic Astrophysics Work Group and chair of the collaboration board in HAWC. Petra, thank you very much for agreeing to give this presentation, especially doing this in your lunchtime. I really appreciate it. So I got to talk with Gamma Ray Astronomy with the HAWC Observatory in Mexico. Petra, whenever you're ready.
Okay, well, thanks, Carsten. It's a pleasure to talk to you about this. I understood from you that a lot of the people in the group are kind of particle physicists or have a background in particle physics. So I tried to take this into account when I prepared this presentation, trying to give you kind of the gist of the whole context of gamma ray astronomy. So on the first slide, and oh, one other thing is, please interrupt me anytime if you have questions.
Okay.
So on the first slide, you see the title, obviously, and I added a subtitle calling it a view into the non-thermal universe. And I will talk about this a little bit, what I mean by that, in the next few slides in the introduction. What you also see here are typical sources of gamma rays that produce gamma rays. For example, you see on the lower right here a binary system that is a compact star that is circling, or these two objects are circling around each other, and in the second compact object might be a black hole, and they produce gamma rays in a certain in a kind of pulsed version, just due to the orbits they are taking. That's one example. But there are many others. You see something on the upper right next to the title, that's the Fermi bubbles, which you may have seen in the news or something. This was one of the major discoveries from the Fermi Space Telescope. And then on the lower left, you see, on middle left, you see, for example, the very left plot is a picture of a supernova remnant in various wavebands. This is an X-ray picture, for example, combined with an infrared picture and an optical picture overlaid. And then in the middle you see, in the lower middle you see a picture of the Crab Nebula, and that is a picture from NASA. This is kind of an important source for us, and I will come back to that, because this is the source in our field we use to cross-calibrate instruments in order to, let's say, this is the brightest source in our waveband in gamma rays, TeV gamma rays, I should say, and therefore we measure it very well. It has been believed to be fairly constant. So in order to cross-calibrate instruments in our field, we use that to measure flux, for example, to calibrate flux measurements. So on the next slide then, which is some comments on the non-thermal universe. So what it is, what is it what we are looking for? So first off, the question is, what do we know? The second question is, what do so in our galaxy, the energy density in particles is about 1 eV per cubic centimeter, and that is charged particles, and that is approximately the same as the energy in photons, or as the energy that is stored in electromagnetic fields, and that is also approximately the same as the energy that is that comes or that is stored in the universe in the cosmic microwave background. We also know that the nature accelerates particles to up to the greater than 10 to the 20 eV, and we know that through measurements with ultra-high energy cosmic ray detectors, such as the HAWC detector in Argentina, or the high-risk detector or the TA detector in Utah. And then the question now is, what do we want to know? So we want to know which astrophysical sources accelerate these particles. And we kind of know that, but we don't know how many accelerate these particles, what is their exact contribution to the cosmic radiation in our universe, and so on. So we essentially want to understand it better, and hopefully we'll be able to do probably not precision physics like at CERN, but we want to be better in our predictions or our understanding of these this cosmic accelerators. Then the other thing is, the question is, how do these astrophysical sources accelerate particles, and what are the mechanisms how these particles are produced? And then once you understood the first two questions here, then the hope is that we will be able to measure or get a better grip on high energy phenomena or phenomena of fundamental physics, such as dark matter and things like that. I have a slide on that. I give you a few examples of later of what you can measure. And to the right here, you see this this plot everyone has seen, and it's kind of summarizing what I said on the left, because yes, we measure cosmic rays, we measure the flux of cosmic rays across a long energy band, a broad energy band. But the question is, you know, why does the spectrum look the way it looks? And the question is, you know, when, for example, do we measure galactic cosmic rays? When do we transition to extragalactic cosmic rays? And again, what are the processes that accelerate these particles to such high energies? And you probably have heard of the knee, which is, and the ankle, which are both features that change the spectral index of this flux of cosmic rays. Okay, so why? So this is before here. So I for the most part spoke about cosmic rays. So why do we measure gamma rays? Why is that interesting? Because in fact, actually, when you look at the flux of gamma rays that or the local flux that we measure here, it's a lot smaller than the flux of cosmic rays. It's about 1 in 10,000 showers we measure with our HAWC detector is a gamma ray, or is caused by a gamma ray. So the reason is actually a very simple one. We have galactic magnetic fields, and so if you look especially at lower energy cosmic rays, they will be deflected by those, and they will not point back to sources. And this slide 3 is what I'm trying to show here is exactly that the gamma rays come directly from the sources, are undeflected, and therefore we can actually resolve source. When you do look at maps of cosmic rays at our energies, that is TeV energies, you will not really see structure. Well, which is not quite true. We see some structure, but it's not. It's kind of a diffuse structure, but no sources. Like, for example, one of the questions is in our field is, cosmic rays mostly accelerated in supernova remnants, and they are very small objects in our maps. They are less than, you know, half a degree wide often, and those would not be resolved with cosmic rays. And this is why in our field it has become very popular to talk about multi-wavelength astronomy, and also multi-messenger astronomy. And in this slide here, I show also the neutrino contribution here. Neutrinos, just like gamma rays, are produced in hadronic interactions of those protons in these sources, and therefore they also are good, are different messengers, so not electromagnetic, but they are good messengers in order to look for sources. But the problem there obviously is they are very hard to detect, as you know, and also the statistics is a difficult one. But, you know, we are making progress there. Okay, then on slide 4, I'm giving you the examples as to how gamma rays are produced. So gamma rays are, like I said, probing the accelerated particles in these sources, these charged particles that are accelerated. And we usually distinguish 2 types, electrons and hadrons. And the electrons produce gamma rays in 3 or 4 different production mechanisms or TeV gamma rays, I should say, GeV to TeV gamma rays in 4 different production mechanisms. One is synchrotron emission. Obviously, when you have a charged electron circling around a magnetic field line, then it will produce synchrotron radiation, and those are gammas that we measure. Then inverse Compton scattering is that electrons interact with the background radiation, such as, for example, the cosmic microwave background, and the photons of the cosmic microwave background are getting upscattered to TeV energies and below TeV. Then synchrotron Self-Compton is when these upscattered photons again, when the photon field again interacts with the electrons. So you get a kind of a doubly synchrotron effect from that, and that will increase your flux of gamma rays. And then there's Bremsstrahlung. So if there's gas or matter somewhere in the universe, then if you have a proton, if you have an electron going by that material, it may interact and produce through interaction with the ions of these of ionized gas, for example, it will produce gamma rays as well in the Bremsstrahlung process. And then the hadrons, I don't have to tell you much about that. You know much better how these particle physics reactions happen. But you know, of course, proton-proton interacts and produces pi plus, pi minus, whatever, also pi zeros, and these pi zeros decay, as you well know, into gammas, and those gammas have TeV energies of matter energies. So on slide 5, you see the galactic and extragalactic sources of gamma rays. So these accelerators we are looking at, I already talked a little bit about the Pulsar Wind Nebula. Those are electron-positron nebulae that may interact with the microwave background and things like that, thus producing gamma rays. We have pulsars. Those are at the center of these Pulsar Wind Nebula. They are fast-spinning neutron stars, very, very heavy, more than the sun, the solar mass, but very small. For example, the Crab Nebula is believed to be of the size of 30 kilometers and heavier than the sun. So you can imagine that's a very heavy object. And as it spins, it produces a magnetic field, or actually it's the pulse effect happens when it spins not along the magnetic field lines of that star, and thus producing a cone in which particles can be accelerated and produce electrons, which then we will measure. And since they are spinning, it produces kind of a lighthouse effect. So a lighthouse that is striking, you can imagine, Earth, and then we get an enhanced gamma ray flux, and you know, at a periodic term, and the fast is like 30 milliseconds or something like that. So these are very fast spinning neutron stars. Then supernova remnants are believed to be producing gamma rays in these hadronic and leptonic interactions, as well as particles as the shock front moves out and interacts, and in this shock front, as the shock front moves through space, particles are accelerated, and then through interaction again with matter, for example, or the cosmic microwave background and other things, will produce gammas. And then we have X-ray binaries that I mentioned at the beginning. Extragalactic sources are active galactic nuclei, so they are usually where you have galaxies that are at the core of the galaxy is a black hole, a spinning black hole. Around it is an accretion disk of material. As the material falls into the black hole, it produces jets in both directions of particles. So essentially the gravitational energy is converted into energy that accelerates particles. And then we have starburst galaxies. We have long gamma ray bursts, a burst of gamma ray or gamma ray flashes that are larger than, where the duration is larger than 2 seconds. It is believed that this could be red giant stars, for example, collapsing onto its core, and then they becoming so dense that they expel outer layers into the supernova explosion, and that in the end will lead to jets, very much like I explained for the active galactic nuclei. Then we have short gamma ray bursts. Again, these are believed to be two objects such as very compact stars, for example neutron stars, that circle each other, then they begin to spiral inward and eventually collide, and thus again produce these jets as I explained them, a very similar scenario as I explained them for the active galactic nuclei. Okay, what about fundamental physics? There are three main fields of three main contributions gamma ray astronomy can make to fundamental physics. One is in cosmology, and I'm not going to talk much about this, but the measurement of the attenuation of gamma rays by infrared photons tells us something about the evolution of the universe. In particular, you can, using, for example, active galactic nuclei, and if you kind of know the distance, there are certain measurements, distance measurement of obviously from other wave bands, you can then compare those for close by that you think you understand and far away, and then if you assume the same model for them, you can look at the flux you see at Earth, and applying models, you can then see how opaque the universe is to these faraway sources, or for gamma rays from these faraway sources, and that allows you to draw conclusions about the extragalactic background light. Then there's Lorentz invariance. That's kind of I don't know, new topic, but it's a topic that people become more and more interested in. That essentially is trying to answer the question through photon of different energy travel at different speeds from distant astrophysical transients. So a popular source of that is, field of study here is gamma ray bursts, because we believe if you assume that the photons are produced very close by from these flashes, and then you look at the time difference, you may be able to draw conclusions about Lorentz invariance violation or things like that. But that would be only one source class. Another source class would be pulsars, and people are looking now for pulsars as well for similar effects. So the idea here is just like in particle physics, that you, by looking at different accelerators, such as pulsars or gamma ray bursts, that you become independent of your model assumptions, or more independent of your model assumptions, and more independent of, in general, systematic effects. So if you, let's say you find some kind of Lorentz invariance violation effect somewhere in gamma ray bursts, it's very difficult to prove that it's really true. But if you find it in pulsars as well, then the argument becomes a lot more compelling. And then there's dark matter, and this is probably a lot of you have heard about that. AMS has measured a positron excess, and in fact, I think that was presented also at the ICRC in Rio a couple of years ago, or 3 years ago now. And often people then immediately point to dark matter for this, and that maybe WIMPs annihilate or so, and produce this excess of positrons. And I will talk about that, hopefully, if I have time, a little more in later slides, and try to make the case why it's important to do this botany of gamma ray astrophysics in order to really make well-founded claims about dark matter detection. So one last comment on the non-thermal universe. So here on slide 7, I show a poster that you may have seen. It's a poster from NASA from 1996. And on the next slide, I show this poster with measurements added at the highest energy band, that is TeV gamma ray, TeV gamma rays. And you see two measurements here. You see the Milagro, and I'm talking a little bit about Milagro, not much, a predecessor of my experiment, my current experiment, HAWC, in gray, and then you see the newest, latest measurement from the HAWC Observatory in Namibia. And I will show you where these two observatories are in a moment. So what you see again is here the galactic plane in various wavebands, and that's what is exactly what when people are talking about multi-wavelength astronomy. The idea is to, or the goal is to combine the information from all these wavebands, because they are often, as you look along the different wavebands, you see there are sources, common sources in various wavebands, and so the goal is to understand them across the broad electromagnetic spectrum. Okay. All right. And oh yeah, and the other thing is, I say, and the non-thermal universe. So really, gamma rays are the window into the non-thermal universe. A lot of the other stuff is really produced in thermal processes. So you are touching, or you're probing a different phase space of these sources by looking at gamma rays. Okay, so any questions so far?
Not here. No, please don't. Continue.
Okay, I will continue then. So observatories. Again, here I give you, in this slide, I give you an idea of the observatory. Then you see the electromagnetic spectrum, and then you see different telescopes. And to the lower right, you see a plot of the that shows the opaqueness of our atmosphere for different wavebands. And you see, for example, if you measure stuff in the visible, here shown here with the rainbow, then you know that you can do measurements as long as you are in dark areas and there's not a lot of light pollution. You can do measurements at Earth. But for a lot of the other things, like to the left there, you see gamma rays, and that only goes up to Fermi experiment, to energies, GeV energies. You cannot measure these gamma rays at Earth because they will be blocked by the Earth atmosphere, and the same is true for various other wavebands. One other ground-based way of measuring radiation from these astrophysical objects is, for example, radio. And you probably have heard about the VLA in New Mexico and other places where they measure radio emission. Okay, so on the next slide, I just replaced that spectral plot, or that opaqueness sketch with one of the TeV gamma ray instruments. And that leads me right away. This is the HAWC instrument. You see 4 telescopes here. And then you see HAWC2, which is the latest edition. It's actually quite monstrous. It's 30 meters in diameter. And they are able to move this in the matter of seconds. So tons of material are moved in the matter of seconds. This is actually really quite impressive. Then on slide 11, you see the gamma ray instrument, the various gamma ray instruments that we at the moment in our field have at hand to do measurements with and to do research with. There is number 1 to the upper right, you see the Fermi Space Telescope, obviously, but there are other space telescopes such as Agile, which is led by researchers in Italy, but it's also an international collaboration, obviously. Then you see to the right again, at Earth, the Argo YBJ instrument. It's a ground-based detector that measures, that is a particle sampling detector that measures air showers that are produced by gamma rays, and a little more on that in the following slide. Then you see HAWC in Namibia. So the Argo instrument is in Tibet. You see HAWC in Namibia. You see MAGIC on the Canary Islands, and then you see Veritas in the northern hemisphere in the US, and Milagro was just north of Veritas, but it has been shut down since then. It is again the predecessor of HAWC, which you then see here which is in Mexico, located in Mexico, closer to the equator. Okay, now what's the idea of these gamma ray detection techniques? Again, in the sketch here, that's an old sketch, but I like it because it's very simply explaining what the different telescopes do. So you see to the upper right here, you see just like a sketch of the EGRID space telescopes, and you see here the detection area, which is less than a square meter. It's a little bigger for Fermi now, but it's comparatively small, and you probe up to 10 GeV now with Fermi. Actually, it has they go to hundreds of GeV gamma ray energies, and the latest even to TeV energies. They have improved their analysis so much. And then you see the Ash-Renkov telescopes that make use of the Earth atmosphere, and they actually measure the Cherenkov light that is produced by the gamma ray showers. Again, as particle physicists, it's not news to you. Gammas or protons, as they enter the Earth atmosphere, they will interact with the nitrogen molecules mostly, and produce air showers just like you would in a calorimeter. And that's what people often say, that the Earth atmosphere is used as a calorimeter to detect these gamma or cosmic rays. So the thing here is that the optical detector can detect these showers as they are evolving in the Earth atmosphere, while the particle sampling detectors to the right here measure only the shower front as it arrives at the Earth's surface. So there are drawbacks and advantages to these techniques, and I will also talk about those in the next slide. To the right here you see a simulation which shows the number of particles versus the atmospheric depth, and it shows that the maximum number of particles in an air shower is reached above just below 6 kilometers. So clearly, if you are not an Ash-Renkov telescope, then rather a particle sampling detector, you would like to be as close as possible to this peak, because it means that you have more information about the shower for everything, for measuring the energy, for measuring the angle, the direction of the shower, everything. So that brings me to slide 13, which shows various gamma ray detectors and their strengths and weaknesses. So we have the space-based tracking detectors, Fermilab, Agile, EGRID. They have a wide field of view, rough 2.4 steradians, and roughly a uniform exposure of the entire sky in survey mode. They are continuously operated, and they have a very low background. So it's essentially a particle detector, a sandwich detector with heavy material and scintillation counters that produce, like the gamma ray enters the heavy material, does pair production, then you track the electron-positron pairs in that. And you have surrounding the detector, you have an anti-coincidence field, again a scintillator, which allows you to say, okay, that was a cosmic ray, otherwise it would just go through. The drawback is that the area is small and limited, and therefore the observations at highest energies are very limited. And then you have moderate angular and energy resolution. Then you have imaging Ash-Renkov detectors, such as the ones the aforementioned Veritas has, Magic, Petra, and Whipple is the earliest of those. And there the angular resolution is better. The large area allows them to measure TeV, cosmic and gamma rays, and they have a very good rejection rate for background from cosmic rays. Like I said earlier, 1 in 10,000, about approximately 10,000 showers is only a gamma ray. So you have to have a good way of rejecting those cosmic rays if you want to drag out those gamma rays from your data. The drawback is that you can only do pointed observations with a small field of view, less than 5 degrees. and that you also have a low duty cycle. So you can only run on clear moonless nights. And they had done some stuff in order to be able to observe with the moon somewhat up, but still essentially it's really only a 10% duty cycle. And then you have extensive air showers arrays, that is such as the HAWC detector, the Tibet air shower array, Argo, and Milagro. They have a wide field of view, about 2 steradians, and depending on where they are located, they see the northern sky or the southern sky. They are continuously operated because they are not, they are measuring, they are using things like scintillation counters or the water Cherenkov technique in order to measure the shower particles. And they have a large area, just like before they use the Earth atmosphere essentially, and therefore as a current, and therefore they have a much larger area. They have, however, not such a great angular resolution and energy resolution as the air Cherenkov detector, and they have a moderate background reflection. So that brings me to HAWC. So you see here a map of Mexico, and there's a tank, a little tank as we call them. And that's where the detector is located. It's about, the location is 19 degrees north, 97 degrees west. It's on the Sierra Negra Plateau near Pico de Orizaba in Mexico, which is the highest mountain in Mexico at 5,600 meters. The detector is located at 4,100 meters above sea level. Again, go back to the shower simulation. We do that because we want to be close to the shower max. It contains 300 detector stations. Like I said, we call them tanks. They are pretty humongous, actually. 7.3 meters by 4 meters high, 4.5 meters high, and they are filled with water. And I show you a picture of that in a moment. The area is 22,000 square meters. The water volume per tank is 200,000 liters. So do that times 300, and you arrive at a very large amount of water that had to be trucked up the mountain. A third of the array had been online since 2013, and I will present some results from the early the partial array data. And then we have the array is now complete, and there was an inauguration ceremony in 2015 where even the NSF director showed up, and the director from CONACYT, the Mexican funding agency. So that was a very rewarding event, actually, after such a long time. And here you see a picture of the HAWC array, and this was done by one of my PhD students, actually, and you see the kind of Photoshop in the HAWC sky with one of our first results. Okay, so then I show the site as it progressed through time. So the lead time for our experiments are long, but certainly not as long as anything like in particle physics. But still, it's been more than 10 years coming until we finally could take data. So you see here the HAWC Observatory site in Google Maps from in 2006. On the next slide, you see it in 2011. So you see here on the left, upper left, that's an engineering array. We call it VAMOS. NSF gave us some money in order to demonstrate that we actually can operate a detector at such a remote area and get some data out of it. And this is what that is. Then we have 2011 only in May. Before that was in January. So in May, you already see how the main site is getting prepared. Then in 2011 in October, we already have almost one third of the array done. And here is the counting house in which all the computer equipment and electronics is. So the way it works with HAWC is that we run out cables to the photomultipliers in these detectors, and then read out and combine the data at this counting house in the middle. Then we have a picture from 2013. So a lot more data tanks have already been installed, and many of them were equipped with photomultipliers already. Oh, and I should mention to the right here is the HAWC utility building, So I told you it's a water Cherenkov detector. So in this HAWC utility building, we have a filter. Um, um, uh, we have a filtering station which allows us to filter water at the site before it gets filled into the tanks. And then we have the full array pretty much at the end of 2014. This here on this next slide here, that's the HAWC collaboration, and it's at a meeting in 2013 that we had here in Houghton. So you see how beautiful it is. So HAWC is about 100 people strong, plus or minus, and it used to be a Mexican American collaboration. Since then, we have new collaborators who joined us from Poland. One collaborator and another collaborator, another group from the Max Planck Institute in Heidelberg is involved now as well. And they are both involved in HAWC as well as in CTLA and also now in HAWC. Okay, so how can HAWC be so much more sensitive than Milagro? So this is a picture of Milagro. In Milagro, we had a pond filled with water, and in that pond, we had two layers of photomultipliers. One is called the air shower layer. The other was called the muon layer. The muon layer is called that because it was more deeply immersed in the water, and therefore it measured light from water Cherenkov from the particles traveling faster than the speed of light in the water. Then it usually is from muons because they survive longer rather than electrons, for example, that will do pair production or whatever as they enter the water much more likely. Then so how can it be so much more sensitive? So there are several reasons. One of them is that the Milagro collaboration, you see the picture of the collaboration here, is much smaller than the HAWC collaboration. And I know you're probably, as someone who works on Atlas or CMS, I guess, you're not very impressed by the size of the HAWC collaboration, but there is a big difference. We were like less than 40, maybe around 30 people working on Milagro, and now we are more than 100 on HAWC. So that helps, of course. People power helps quite a bit in doing a better job in simulations and data algorithms and things like that. Okay, now other reasons that the system has improved.
Petra, hi, sorry to interrupt you. This is Helena. Just a quick question. Is the Milagro detector still operating?
No, it has been shut down in 2008.
Okay, thanks.
Yeah, so all the people have moved from Milagro essentially to HAWC, most of them anyway. Some have moved to other experiments, but a lot of them, the bulk has moved to work on HAWC.
Okay, and how big, more or less, is the HAWC collaboration? Like about from the picture 100?
Oh, at the picture we had probably 70 people showing up for that. But yes, it's more like 100 in total. You know, sometimes the thing is it's sometimes not that easy for Mexican collaborators to travel to the US.
Yeah.
It's a question of money, and you need to get a visa and all these things. But
yeah, I can imagine. Okay, thanks.
Okay. All right. So three main reasons, other than the size of the collaboration. The altitude makes, and I have mentioned that numerous times before, so I'm not going to say much, but we have about 5 times more particles, detectable shower particles, relative to Milagro. You see here Milagro on the right is at 2,600 meters, HAWC is at about 4,000 meters. And that is, if you see here the effective area plot to the left, it helps us in particular at lower energies. So we become more sensitive at lower energies because we get more particles. So we are able to detect and reconstruct showers. Then number 2, the hadron rejection area and the shower sampling area has improved. So we have now 10 times larger muon detection area. Here the trick is, so you see here in grayish, the gray box kind of trying to indicate the size of the Milagro bottom layer size again. about detecting muons. We measure, or we distinguish between hadrons and lepton or gamma ray showers by the muon richness of the shower. So, and I show that in the next slide here. So proton tagging, you see like a little sketch of a cosmic ray proton shower. And again, as particles physicists, you know that you get all sorts of particles. There are mesons, muons that travel faster, etc. And will again interact with the Earth's atmosphere and then end up producing electromagnetic subshowers. So what you end up finding is shown here in this event picture of the HAWC array. So you see here, this is a proton plot, and you see the detector array, and you see the size of the circles here show the size of the signal in the photomultipliers in these showers, in the detector. And what our reconstruction algorithm does is it tries to reconstruct the shower core. That is where the particle, the cosmic or gamma ray, would have hit the Earth's surface would it have not been interacting with the Earth's atmosphere before. So kind of like yes.
There's a question here.
What is a muon for you, I mean, in the sense of the signal? How do you distinguish a muon from a bunch of photons or electrons coming into the tank?
Yeah. So that's the idea. So we don't distinguish muon quite yet. People are working on that, but the idea here is, so you reconstruct the shower core. You see that is kind of here. Then you define a circle, and that is all optimized using Monte Carlo simulations and actual data, because we can assume safely that most of the data is cosmic rays. And then you look at large signals outside of this circle, right? And that must be far-traveling muons, for example, is the idea here.
Okay.
Right. So, and I can go to the next slide here, actually. So, electromagnetic shower, gammas. We assume gammas don't produce muons, even though they sometimes do. But here you see like a much more confined shower. Right. So this is clearly a gamma shower. This is in fact a simulation. Also, and so you see barely any signal outside of this circle. Does that answer your question?
No.
Okay. Yeah, I had a animation, but I decided to go with the PDF file, so I didn't put that into the presentation. Okay, so finally, we also have an improved angular resolution and energy resolution. Again, that has to do with the altitude. Really, all of these things, we mostly really profit from the high altitude because we get more information about the air showers. But also, it turns out that if you compare this to the Milagro detector, the optical isolation of the detector elements actually helps. So in Milagro, we had a pond filled with water. Now we have these 300 tanks. Each has, here you see only 3 PMTs, but we now have 4 PMTs. And so you get much better information about where the particle actually hit the detector, the charged particle. So in the next slide, you see actually a picture of this. So this is just a sketch, and here you see a picture of the elements of this detector. So inside of the detectors that you saw on the photo of the detector array is a bladder, what we call a PVC bladder. Inside that, we just fill the water, and and fill in the water, and inside the water we put in the photomultipliers. And we use 3 Hamamatsu PMTs. They are 8-inch wide, and we use 1 Hamamatsu, which is 10-inch. And these are immersed in the water and measure the water shrink of light. And then in the next slide, you see a tank where the bladder is already inside, and you see how kind of the dimension of this thing. And this is our former collaboration leader, Brenda Dinges, who was, up until last year, she was the leader or the spokesperson of the collaboration. Okay, I swap over, well, timing calibration. Well, you need to obviously understand the timing of these photomultipliers. relative to each other, because the way you reconstruct the direction of the shower is by reconstructing the shower front. So if to the right here you see an event picture, and the color scale tells you something about the hit times. So this is early and this is late. So blue is early and reddish is late. So you can reconstruct the shower was coming from this direction. That's the principle of it. This is, of course, a little more complicated in detail. The flux sensitivity of HAWC compared to other instruments is shown on 32. So what you see here is the differential sensitivity per quarter decade of energy, and then versus energy. So we measure everything that is above the blue line here. That is for HAWC 300 1 year and HAWC 300 3 years. That's all based on simulation. And it looks like we might be even a bit more, from our first analysis, a bit more sensitive at the highest energy. And then you see Fermi 5-year at lower energies, the Fermi 5-year sensitivity, and you see the HAWC sensitivity compared to operational Air-Cherenkov telescopes. And so at lower energies, you see that the Air-Cherenkov are clearly more sensitive, although 50 hours is quite a long time to collect if you only have a 10% duty cycle. So it sounds like not a lot, but it's actually you know, a lot, because number one, you have a 10% duty cycle. Number two, these telescopes are pointing, so people have to agree on which sources they point at. So that is indeed a long time. While yes.
The lowest energies you are sensitive towards is 200 or 300 GeV. The question is that you can you measure tails of gamma ray bursts?
Well, that's one of the, that's not my, I don't have much expertise in that, yes, but we have 2 or 3 people working on gamma ray burst analysis, looking, like we communicate with Fermi, for example, and each time they send out an ATEL, then we will look at that. We will absolutely look at that if it was in our field of view, right? But yes, so and it depends a little of, we have like 2 data acquisition systems, if you like. So we have one, which is the main data acquisition system, which works through TDCs, and then we have a second one, which is scalars, where we don't really have any directional information. But if you get a trigger from Fermi, you don't really need that. All you will look for is an excess in the flux measured in the scalars, if you like, in the signal. So and then you can go. Well, I don't know, 100 GeV maybe. Hopefully, I'm not an expert, like I said, but I think it was like that. Ream ballpark. Okay. Did that answer your question?
Yeah, okay.
Right. So then in the next slide you see the HAWC sky coverage. I mentioned HAWC is located still in the northern hemisphere. So what you see here, the white is where we cannot see anything. So unfortunately, and then the gray shaded area, the darker the area is, the better our sensitivity. So we have at the very dark areas, we have about a 5% of the Krebs sensitivity. So meaning 5% we will detect sources that emit 5% of the Krebs flux. Again, the standard candle, as I mentioned at the very beginning. And then at the declination of 75 in the north, we run out of steam, and then also we cut at a zenith angle of 45 degrees overhead, because below that it's getting difficult for us to, I mean, we have to probably work a bit more on our analysis tools in order to do gamma hadron rejection, the more inclined the showers are that we measure, number one. And number two, also, of course, the atmosphere is getting thicker then. So we, in particular, lose at low energies. So we barely see the galactic center. And if we, I think, well, we can probably measure something from it, especially if there's interest in terms of dark matter emission and so on. Then we certainly should put some more emphasis on it. But right now, it is something that we have not really done yet. Okay, so finally, it took me a lot longer than I thought. But finally, we have some results here. So these results have been presented at the APS meeting in April. And what you see here in this slide here is the all-sky gamma ray map as produced with HAWC above 100 GeV. And we see several locations here. We see first off the galactic plane, and then we see the Crab Nebula here to the right. Then we see an emission, a little bit of an emission here near the Geminga region. And then we see, for example, here a source. This is Markarian 501, which is one of the AGNs that we detect. So far, so good. So let me move on. Skip over that slide with the NASA poster, and you see a similar view as you get it with the Fermi-LAT telescope above 1 GeV. And in the next step, you see these two overlaid. So it just goes to show that we do see the same objects, right? And one of the efforts in our field is really to combine the information and measure gamma ray sources from MeV up to all the way to 100 TeV. That's the goal here. Okay, then also I mentioned Fermi-LAT has become a lot more ambitious at the highest energies than its predecessor eGrid did. So they just came up with a map that goes up to 2 TeV. So that's great because that way we will able to we overlap in the energy range, and that will help us again to do combined fits of the sources we are looking at. And then again in the next slide you see an overlay with that. Okay, so next slide shows a zoomed-in view of the galactic plane. Again, Fermi-LAT up to 2 TeV, and you see the HAWC sky along the galactic plane. And I will talk about these three regions: the inner galaxy, the Cygnus region a little bit, and then the Geminga nebula. Over time, I mentioned Milagro. So you see here what Milagro accomplished in 8 years of operation. Then the next map shows what HAWC saw with a partial array. HAWC Pass 1 means only 100 tanks instead of 300 tanks, and we already are a lot more sensitive. One of the things that's to keep in mind here is that Milagro was located just ideal to measure the Cygnus region. This is the Cygnus region, the Cygnus arm of our galaxy, while HAWC is much more south, so HAWC sees the inner galaxy, what we call the inner galaxy, a lot better. And then with the full array, again, now we see clearly the Cygnus region, and we already after 1 year see it better, almost, actually not almost, we see it better than Milagro in 8 years. And we also have resolved a lot more the inner galaxy. So this is a major accomplishment. Then you see here, this is, I think I skip over this. This is just something we presented. This is our first published result. With the partial array data, we measured 10 sources. 8 were associated with other objects in the sky. 5 sources were known, so we saw about 3 new sources. Now, with the full array, again, the picture becomes a lot clearer. We see Markarian 421 at a 31 sigma. We see Markarian 501 at 21 sigma, significance above the background. We see the Crab Nebula at 84 sigma. And then we see this glowing emission along the galactic plane. And this is not really published yet. We are working on a publication, but it looks like we probably have about 40 sources that we detect. And you see, if you see the overlapping emission here, then you see that a lot of the work will go into distinguishing how many sources, for example, we see. Do we see 1? Do we see 2 overlapping sources? Are these sources extended? Are they point sources? This is kind of what our main analysis at the high level goes in. And then, okay, I'm gonna not talk too much about these sources here. Let me skip over this. Like I said, we saw new sources. We see the Cygnus arm of our galaxy. Let's talk a little bit about one particular source. that is the Geminga source. And I mentioned that at the beginning, that there has been a positron excess measured by Pamela and by AMS later on. And there was a paper after the Pamela result came out from 2009 that said, well, you know, it doesn't have to be dark matter. It could be just Geminga, which is just close by enough to produce, it accelerates plus E minus to produce a local excess of positrons. And then in 2006, in 2016, now again, we measured Geminga with HAWC, and we are currently working on a publication trying to understand the emission of Geminga at highest energies, and from that draw conclusions of how they were produced and how many positrons and electrons it will take to produce them. For that, we take into account what we know about Geminga and how far away it is. We also detected, also unprecedented, we most likely detected another pulsar, which is very similar to Geminga, and also may contribute to this this positron excess. So the question is, do we live in the positron bubble from these two pulsars, or pulsar wind nebula is the question, and maybe that is what is producing this anomaly in the positron flux. I will skip over the next few slides about this and just say a few words about really large structures. So I think we are now on slide 50. So as I mentioned previously, the Fermi bubbles have been measured at Fermi energies, and so the question was, do we see something at TeV energies? And this is interesting because the question again here, is it electrons that produce the gamma ray flux, or is it protons that produce the gamma ray flux? And we think these are relics from the jets that came off from the galactic center, from our galactic center back in the day. So in order to understand the mechanisms and also the energy content in our galaxy, it would be interesting to study this and to understand that. So let's move to, so there are various plots here, and again I'm running out of time, so let's skip over them. But let's just look at this upper limit plot. So it looks like we are not seeing the Fermi bubbles at our energies. These are the seven upper limits that we were able to calculate at highest at the various energies between about 1 TeV and or above 1 TeV, about more like 10 TeV. So again, it means we don't see them. It does not look like, therefore, that the emission from them is due to protons, because electrons, we think, lose energy before they can even produce TeV gamma rays. We think they lose energy in other processes. So it looks like the leptonic nature is plausible for these Fermi bubbles. Okay, but let's move on. There has been a major improvement or increase in the number of sources. I just pick out maybe the number of total sources, 271 during in the 90s from the eGrid catalog. Now we have 3,033 sources. So why is this important? Again, by the way, we see the same thing at TeV energies. In 2001, we had a mere 10 sources, and now we are approaching 200 sources. So why does this matter? It matters because the increase in the number of sources allows us to classify them, to really look at source class, to look at, you know, something that's co-located with supernova remnants, with pulsar wind nebula, etc. Then with the increase in the diversity of sources, it also allows us to understand the kind of the traditional processes better. And because the increase in the sensitivity of our instruments allows us to study the production and acceleration of cosmic ray particles more precisely, it will allow us finally to look really at new physics, you know, to look at things like dark matter, more precisely to look at Lorentz invariants, things like that. Okay, so there's room for improvement, obviously. In this 59, slide 59, you see the X-ray, the gamma ray, and the very high energy gamma ray world. And what you see is the years, and you plot it versus the years is the number of sources. And clearly, we're still far away from the thousands and thousands of sources that produce X-rays. We are also quite far away from the 3FGL catalog number. But the idea is with new telescopes such as CTA, we will be able to measure much more sources. And I will not talk much about CTA. It is a new, it's an imaging atmospheric Cherenkov telescope that will allow us to, again, to increase the sensitivity. It will consist of 3 sub detector components for low energies, medium energies, and high energies. So essentially what you do is build an array of imaging Cherenkov detectors. And in this slide you see how it improves the sensitivity. So for 100 hours of CTA you get unprecedented sensitivity at MEV up to, at GeV up to TeV energies. So this will be a major improvement, and it will lead to, we think, probably a factor of 10 in increasing source population. LASO in China is another instrument. I'm not going to go into detail about this, but I want to say a few words on HAWC South. So the idea here is to take HAWC to even higher altitude and also to further south. So what our simulations tell us is that we will get a factor of 4 increase in sensitivity between ALMA altitude and HAWC altitude. So again, it will help us immensely in detecting new sources and also transients. And the idea here is if we have a southern side for HAWC, the HAWC South could serve as a source finder, a TV source finder for CTA South. And it will also allow us to measure better the galactic center. And again, all these instruments, the imaging Cherenkov, are pointing instruments. So what you gain with HAWC is the increase in measuring transient events. So things such as gamma ray bursts, although we haven't seen them at our energies quite yet, but other things like binaries and so on will allow us to do these measurements. And these are my conclusions, so I think I've talked enough. So let me know if you have any questions. Sorry about the length.
No, Petra, thank you very much. That was perfect. Thank you very much for this very nice presentation. Other questions here or online?
I may have a comment. Actually, there is a different plan, not a group associated to HAWC, but there is a group which is associated to AG plus Argo of putting a detector which is different from yours in nearby ALMA. There's a region there which is 5,200, which is belongs to Conacyt, Chile, not belongs to ALMA. And one of the ideas of this detector, which is called lattice, is to push down the limit of sensitivity, and we believe we can go as low as 100 GeV, so as to be able to connect with the sensitivity of Fermi lat on gamma ray burst, region where they cannot see anymore. So there is this idea which is also flying around of building, but not using. The idea is basically using RPCs plus a very small water tank, probably ice tank, because temperatures there are very high, are very, very low. I mean, this is normally below 0, so perhaps you have to deal with using ice and not liquid waters.
So, yeah, I heard about the RPC idea. That's true. I think it's good. I think, in fact, to have different approaches, right, to detect something is I think, what people have been doing in particle physics over the years. And I think sometimes in our field, people say, "Oh, this technology is better than the other," and so on. But I think what we now find more and more is that there are complementary techniques, and it's very important to get independent and complementary measurements of the same thing in order to really have good measurements. So do you have like workshops or something that you're planning to do that?
Well, I'm presenting, there is a workshop on that which will take place in Lisbon in October. I think it's October 6 or 7. I can send you some message on that. There is a paper which we are going to submit to publication very soon. Actually, we have, I think probably your colleague Garcinis has a copy of that. Exactly arguing that one can go as low as 100 GeV.
Right.
But there will be a workshop on that in Lisbon. It may be 9 or 10 of October. It's a Monday and Tuesday of beginning of October, which will take place in Lisbon. I can send you, if Carsten send me your email, I can send you an email. And say hello to David Nitz and also to Brian Fick.
Yeah, I will do. Yeah, that would be great if you could send that to me. I wonder if that was already sent around, because within HAWC, in particular, Michael Devenoy is looking at HAWC South for now. But I wanted to get into it too. I have been pretty busy with the HAWC as is, but in the near future, I want to get more involved in HAWC South, because I think it's really a worthwhile effort. I will tell Dave and Brian that you said hi.
Okay. Petra, since you pointed it out, the collaboration size of a gamma ray experiment, of observatory experiment, compared to an LHC experiment, can you say a few words about the actual operation? I mean, how does it work? There's a control room on site. Everything is remote. You have a ground crew that checks every once in a while. And the other question I asked was concerning the possible synergy between experimented LHC and gamma ray physics. Is there something you would like to see measurements constraints from LHC to improve your measurements, or where do you see gamma ray measurements could improve search for new physics at the LHC?
So first off, as far as the operation, yes, I mean, it used to be up until last year that we had usually people at the site, and just like, you know, with, in fact, kind of like with Opal, and I assume now with the Atlas, although you have plenty of people, I guess, but with Opal, you know, we calculate the number of shifts someone has to take, or a group has to take based on how many group members are on the paper. So people were at the site physically. Now, after it has been completed, it's often operated remotely, really, because there's no activity in that regard. But that's not quite true anymore, because I took out a slide about an extension of HAWC. So, in fact, the former spokesperson, Brenda Dinges, she was able to secure some funds from Los Alamos to build more detectors. So right now we are in the process of building a so-called outrigger array, that is an array of smaller tanks surrounding the central detector array. And that helps us with, especially with our sensitivity at highest energies, because we simply have a larger detection area, and that helps us measuring higher energy showers better. So now we are back to this, that people actually are at the site more frequently again, because these tanks have to be installed and have to be cabled up and things like that. But in principle, the array is operated remotely and has been running pretty stably over the last year. So I think we had an uptime of better than 95%. There are sometimes power outages and things like that, but usually they are detected early. Sometimes the detector restarts itself or someone just needs to intervene. But other than that, I mean, it's a way less complicated detector to run, right, than particle detector. So you really don't necessarily need someone there all the time. So, for example, people don't stay overnight necessarily, even though obviously we take data overnight. And then the second about I think there is a synergy. A lot of it is I think so in I guess two ways I could think of right now. One is obviously our shower models that are the cross sections and things like that for the hadron showers in particular. Of course, use data or extrapolate from data that is collected at the Large Hadron Collider. Especially, of course, I think forward measurements are important here. And then in terms of measurements such as, you know, dark matter and so on, of course, when people run these models and they see an excess and they say, okay, this might be dark matter, then they run sometimes Pythia in order to calculate a cross-section and then a flux from a certain process. So it matters obviously what kind of upper limits or what the phase space is that has been set by the Large Hadron Collider experiments and the Large Hadron Collider.
Okay, thank you.
Mm-hmm.
Self-restarting detectors, that's something we need as well.
Oh, yeah.
Are there more questions? That doesn't seem to be the case. Petra, thank you very much again. That was really great. If you have a chance, can you email me a copy of the slides?
Yes, I just looked through. Some people in the collaboration are nervous about certain things.
Sure. No.
I think I only used vetted plots, so I can probably send you the whole thing.
No, whatever you think should be taken out because of, I don't know, political reasons.
And I tend to have large presentation slides, but you know, in terms of size. So I will take a look, but I send it to you. Yes.
Okay. And I guess that if there are other questions coming up, we can forward them to you.
Yeah, for sure.
Okay. Well, thank you very much, Petra.
Okay.
A few more words concerning the next seminar. The actual seminar should be on July 1st. That doesn't take place due to time constraints. The next one will be July 15th. We still have no speaker yet there, so if people are interested, we have an open slot there. Then we have August. I don't think that we have seminars there due to the. I think we should take a break during the Olympic Games. So, but then we will restart in September, October. And the very first talk, one of the very first talks will be. It's already confirmed. The date still needs to be confirmed, but it's already September, October. Will be about silicon detectors and particle physics, and with a special view on radiation hardness and radiation damage. So yeah, as always, if you have questions, comments, please let me know. If you want to present something, your work, your paper you just read, please let me know. We can arrange definitely a time slot. If there are no further questions or comments, then I would say, Petra, thank you again. And next seminar then in 4 weeks, July 15th. Thank you.
Okay. Bis bald.
Bye.
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 Bye.